I'm recording. Don't say anything about that. Olivia or Addie. Okay, so we're doing theoretical probability today. Okay? Very simple. Probability means what? What's the first word that comes to your mind? Starts with a C. Chance. That's the first thing probably should pop in your brain. So probability is chance. And if you talk about theoretical probability, it's basically saying, like, in theory, what's the chance of something happening? Okay? So, flip a coin, right? What's the chance? What's the probability, the theoretical probability that it lands on heads? 1 out of 2 or 50%, right? So that's what we're talking about today. Okay, it's not experimental probability. Experimental probability we will talk about, and experimental probability is based on actual data. Okay, you flipped a coin 100 times. What was the probability it landed on heads? Well, you're looking at data. So there is a difference. Okay, so here we go. Theoretical probability. Probability is the measure of how likely an event is to occur. Occur. When we talk about all of the possible outcomes in whatever scenario that we're looking at, those possible outcomes are called our sample space. Okay? For equally likely outcomes, theoretical probability of event, or probability of event E, is the ratio of the number of favorable outcomes to the total number of outcomes. So over here on the left side, here's what I want you to write. What mathematical operation is ratio telling you? What mathematical operation is ratio referring to? Huh? Division. So we're dividing, and we're dividing favorable by total. Go back to the example that y'all just answered a second ago. I flip a coin. What are the total possible outcomes of flipping that coin? 2, right? That goes on the bottom. But I specifically said, what's the probability that I flip that coin and get heads? Well, there's only one head. So it's 1 out of 2 total. Favorable over total. So you will never have one that's over what percentage? Yeah, in theoretical probability, there's no chance that you get something over 100% of the time, right? So like in football, they say, oh, give it 110%. In theoretical probability, is that even possible? No. Okay, 100% is the highest you can do. So there you have it. Some of these are very simple. Some of them take a little bit more thought. But y'all said y'all want to go fast, so I will. Okay? A jar contains 32 red marbles and 28 blue marbles. What's the probability that a randomly selected marble is red? 1 fraction. Okay? When we think about simple events, we're talking about single events. Single fraction. Okay? 1. So, 2 thoughts. Favorable over total. What's favorable here? 32. Why? That's the red ones. Total is 60. Why? That's right. There were 28 and 32. Total 60. So 32 over 60. What I'd love for you to do is use your calculator. Alpha, y equals number 1. And it'll always reduce for you. What'd you get? 8 out of 15 is our probability. So very simple one, because all the information was just given. You didn't have to think about anything. Number 2, pretty easy. A letter in the word restoration is randomly selected. 1 letter, single event, simple event. 1 fraction. Favorable over total is what you think. Well, what is total here? The word restoration, right? What's total? 11. Where'd you come up with 11? Yep, count them. Now, the favorable is the probability of selecting a what? A vowel. So vowels are my favorable outcomes. So how many vowels do I have? They're A, E, I, O, and U, right? So we got an E, there's 1. We got an O, 2. A 3, I 4, O 5. So in this word, there are 5 out of 11 favorable opportunities. Yes.
What is vowel?
What is what?
Vowel.
Vowel?
Vowel.
Yeah, it's what we call our letters A, E, I, O, and U.
Okay.
Those are vowels.
Vowel.
Yeah.
What would be like B, C, D?
With consonant. Consonant.
Okay.
Consonant. It's like this.
Okay.
Consonant. Is that right, spelling? Consonant?
I think so.
Is that right?
I think so.
That's it. Is that it? Liam, you checking me?
You're asking the wrong group.
It's not constant. Consonant.
This is math.
It's not consonant. It's consonant.
Yeah, you got it.
Boom, I got it. Get off me. I'm a math teacher
I'm not
who's
good at spelling.
brilliant at English as well.
I don't know if you're not that.
I would not be able to spell.
I'm not. So, but I got that one right, didn't I?
You still had to ask
Right. And 5 over 11 will not reduce, so we leave it. Okay, next. A day in the month of January is randomly selected. Okay, stop. What's your total? 31. January is a 31 month. And then, of course, it says, what's the probability of selecting a prime number? Prime.
1, 2, 3.
Actually, weirdly, is 1 prime. Prime is defined as it's a number that's only divisible by itself and 1. And since 1 is itself, 1 is not considered prime. Really. So, what is the first prime number? 2. Then 3. It's 4. 5 is 7. 11. 13 is 17. 19. 23. 21 is divisible by 7 and 3. 20, 29. 31. I think that's all of them. Yeah, that's it. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 31. Will 11 out of 31 reduce? Definitely not. So there it is. 11 out of 31. Let's go down below it. There's a couple things I'd like to make sure you know about a deck of cards. Brady, do you know how many cards are in a deck of cards? 52. It's not including jokers. Those are not really included in a deck of cards. But there's 52. There are 4 of these things that we refer to as, starts with S, 4 suits. Those 4 suits include 2 that are red. What are those? Hearts and diamonds. And then there's 2 that are black, and they are called clubs. They are clovers. You're right. But they're called clubs and spades. So do the math. What's 52 divided by 4? So there's 13 of each suit. Those 13 of each suit are made up of 2, 3, 4, 5, 6, 7, 8, 9, and 10 that are number cards. But then you got Jack, Queen, King, and Aces that we call face cards. Face cards. So, y'all need to know those things. Okay? There could be questions asked about it, and it would be an expectation that you know. So, number 5. What's the probability of drawing a heart or a club? All right, there's another word here that's real key, and that is the word or. In math, ors happen on simple events. Simple events mean single events. But sometimes you have a single event that could be this or that. Well, or in probability means we add. We add. It's still a single event. And the bottom number is still how many cards are in a deck, 52. But what could it be? It could be a heart or a club. Well, how many hearts are there? How many clubs are there? So it could be 26 total cards out of the 52, which is how much? And most of you guys probably saw it and knew it was 1/2. And that's great. But that's how OR works. It happens with single events, and it simply means you add probability. Okay? Single events, simple events, 1. Number 4 is a little trickier. I'm going to do it real fast, though, because that's what you guys asked. I'm rolling 2 dice, but I'm trying to figure out what's the probability that the next roll, so I'm still just looking at 1 roll, is at least 9. Well, here's my possibilities, guys. I could roll a 1, 2, 3, 4, 5, or 6 with the first dice. And I could roll a 1, a 2, a 3, 4, 5, or 6 with the second dice. And what are we wanting to get? A sum of at least 9. What does at least 9 mean? 9's the minimum. Could it be 9? Could it be 10? 11? 12? So it could be anything 9 or above. So here's the deal. Could my first dice be a 1? Is that even possible? Nope, because what's the biggest thing I can add 1 to? And 1 plus 6 is not 9. Could my first dice be a 2? Nope, because 2 plus 6 is 8, not 9. Could my first dice be a 3? If I rolled a 3, what could it roll with? So that's one possibility. How about a 4? Could my first dice be a 4? 4 and 5, but also 4 and 6. So that's 2 more. How about 5? What all could 5 be rolled with? 5 and 4, 5 and 5, and 5 and 6. That's 1, 2, 3 more. 6 would be with 3, 4, 5, and 6. So that's 1, 2, 3, 4 more possibilities. So in all, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of how many possible rolls? This kind of confuses me. How many? 36. Does anybody know how I got to 36? 6 times 6. Here's why. 1, for my first roll, could go with 1, 2, 3, 4, 5, or 6. 2 could go with 1, 2, 3, 4, 5, 6. 3 could go with 1, 2, 3, 4, 5, 6. 4 could go with 1, 2, get it? 6 times 6. 36 total possibilities. So there it is. 10 out of 36 will reduce, and it reduces down to 5 out of 18. Use alpha y equals number 1. Okay, any questions with simple events? Next, quick concept. Complements. Complements. Sometimes it's best to find the probability, what it can be. Sometimes it's easier to find what it can't be. Okay? Sometimes it's easier to tally up all the things it can be. Sometimes it's easier to subtract the things that it can't be. So for example, a complement is the possibility of something not happening. And what did I say the most you could get in probability? 100%. 100% as a decimal is 1. So the probability of not E is 1 minus the probability of E. Well, Smart got 9. I don't like 9 because I wouldn't do not E on 9. I would do E. But I like 7 to just prove to you, because y'all know the answer number 7 without having to do any math on the paper or your calculator. You do this in your head. The probability that it will snow tomorrow is 7 out of 20. What's the probability it won't snow? See, y'all didn't have to do any math. However, I would like you to do this for me. If I want to find not snow, and snow is 7 out of 20, type in your calculator 1 minus 7 over 20. It's just proof that that's how you find not E. Right? You do alpha y equals number 1. So 1 minus 7 over 20, sure enough, what did it give you? Exactly what you knew the answer to be. Okay? Here's the point. Here's where it is useful. I got the next question, number 8. A month of the year is randomly selected. What's the probability of getting a month that does not begin with the letter A? So instead of sitting here and thinking, okay, let's count all the ones that don't start with A. Don't do that. How many start with A? 2 of them. April and August out of 12. So instead of finding what doesn't, just subtract the ones that do. Does that make sense? That's when doing complements is easier. So 1 minus 2 over 12, if you use your calculator, will reduce to what? You got a 5 out of 6 chance.
How does?
Yeah, it's 10 over 12 reduces. Okay? Does that make sense? Okay. Now, y'all just talked about the two dice being rolled. What's the bottom number? 36, right? Liam said. Now listen. How many ways can I get doubles? 6, right? 1 can only match with 1 once. 2 can only match with 2 once. So that's 6 possibilities. So if I talk about not getting doubles, well, 6 out of 36 are doubles. So instead of counting all the ones that are not doubles, let's just count the ones that are doubles and subtract it from 1. So 1 minus 6 over 36 is what? Same as the one above it. Just a coincidence. But there you have it. So complements are when you are doing not an event, it's easier to sometimes subtract the event from 1. Y'all with me on that? Okay. Simple events, what did I say to focus on? Single, 1. Compound events, we're thinking about multiple events. And here's what I want you to remember. Multiple events, you multiply events. Multiple events, you multiply events. You think you can remember that? When I am doing multiple things, multiple probabilities, you've got to multiply those probabilities. Multiplying probabilities make it a lot less likely for it to occur, right? Because if I'm talking about picking a number out of a hat between 1 and 30, if I ask about doing 1 time, that's pretty bad odds, right? But what about doing that same number 2 times in a row? That's even harder odds. So multiple events, you multiply the events. And there's 2 different types. There's independent and there's dependent. Independent means that what you do the first time does not affect what you do the second time. They're independent of one another. Dependent means what you do the first time will affect your probability for your second time. Are you with me on that? So the formula, if you will, for an independent event is you simply take the probability of A and you take the probability of B and you do what with them? You multiply them. Multiple events, multiply the events. Now, dependent is the same thing, kind of. It's the probability of A times the probability of B after A occurred. There's going to be a key word, a key thought that you look for that will help us to know whether it's independent versus dependent. For example, number 11. A die is rolled 3 times. 3 times. Multiple events, what? Guys? Multiply events. How many fractions will I be multiplying here? 3 times I roll this dice. 3 events. Multiple events, multiply the events. Now, how do I know this is independent?
It doesn't matter.
It's a dice, right? If I roll a dice right now and I roll a 1, if I pick that dice up and roll it again, is that dice going to be like, no, you just rolled a 1, I'm not going to roll a 1 again? The dice has no control of that. It's independent. So what was the probability of me rolling a 1 the first time? 1 out of 6. How about the second time? 1 out of 6. What about the third time? 1 out of 6. Independent. So you go 1 out of 6 times 1 out of 6 times 1 out of 6 times, not add, times. Big difference. It's 1 out of 216. Okay? Yeah. You multiply straight across. 1 times 1 times 1 over 6 times 6 times 6. Big difference. Would y'all bet your house on that? If you did, your parents would kill you. Okay?
Wait, so if you did it 216 times, it would happen once?
No, if you did it 3 times, you would have a 1 out of 216 chance of it actually getting a 1 all 3 rolls. Does that make sense?
So, like, if you roll a dice 216 times, there's a...
No, if you rolled a dice 3 times, you'd have
That's what I know.
You'd have 1 out of 216 times of rolling that dice 3 times where you would get a 1
Yes.
every time. So very unlikely is the point. Very unlikely. All right, so number 12 is kind of a silly one, but it represents the idea of independence. A coin being tossed and a day of the week being chosen have nothing to do with one another, right? It's multiple events though, so what do? We multiply the events. So what's the probability of the first event, getting a tail? 1 out of 2. What's the probability of the second event, getting a day of the week that start with T? 2 out of 7. So if I want to figure out what's the probability of those 2 things happening, I multiply those events. 1 out of 2 times 2 over 7. I think I got 1 over 7. Is that right? So very unlikely still. 1 out of 7 is not very good, but it's better than the last one for sure. All right, now here's where you're really going to see a difference. You notice that this question, a bag contains blah, 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 that's under the independent events, but then they want you to use the same example right below under dependent events. So I want you to see the key word here. In the first one, after they describe this bag of crayons, what does it say about a crown being selected? It's replaced. It's replaced. So I put my hand down this bag, I pull out a crown, right? Then I put it back in there. When I go back into this bag, did that first pull affect my second one? Nope, because it was replaced. That makes it independent. But if you look at the next group that's under the dependent events, notice what it says. Assume once a crayon is selected, it is what? Not replaced. So that means I reach my hand down in here into this bag, I get out what I was supposed to get, but I take this crayon and I put it down on the table, and then I reach back into the bag. Did what I just picked affect what I'm about to pick? Yeah, because it's not in the bag anymore. It's dependent. Do you understand the difference? Okay, so here we go. We'll go fast. A bag contains 8. Well, you read it. What's the probability that you get a purple and then a yellow? How many events? 2. Multiple events, we multiply events. Y'all better remember that. If you don't, I'm going to bust you up. So start with the first reach down into my bag. How many crayons are in there? 32. How many were purple? 14 out of 32 chance. You put that crayon right back in. You reach back in there. How many crayons are in there? 32. How many are yellow? So it's 14 over 32 times 6 over 32. So type that in. What do you get? Use alpha y equals, and it'll give you the answer in simplest form. I got 21 over 256. Is that what you got? Nope, that's right. Number 16. The probability of picking how many? 2 yellows. Multiple events, we multiply events. I reach my hand in this bag. How many crayons are in there? 32. How many are yellow? 6. I reach down in there. I sure enough get a yellow. I had a 6 out of 32 chance I got a yellow crown. I put it right back in. I reach back. What's the probability second time in getting another yellow crown? Same. It's independent because I replaced it. So 6 over 32 times 6 over 32. 9 over what? 256. That's what I got too. Now, look at the next group. Next group uses the word not replaced. Same group of crayons. The probability of a yellow and then a red. How many events? 2. Multiple events, dadgummit, say it. Multiple events, we multiply events. Here's the difference. I reach down to this bag that has how many crayons? 32. How many are yellow? 6. But what do I do with that crayon? I put it on the table. I reach back into this bag. Now how many total crayons are in there? Only 31 now. See? Dependent. What I just did affects what I'm about to do. You understand? Now out of those 31 crayons that still remain, how many are still red? 8. So it's 6 over 32 times 8 over 31, which is 3 out of 62 when you type it in your calculator. 2 more. Look at number 20. 2 greens. Multiple events, you know what? I'm not pleased with this. Everybody's about to say it. Ready? Hunter, are you ready?
Mm-hmm.
Multiple events, One more time. Multiple events, Okay. All right. So, 2 greens. I reach my hand down in there. How many crayons are in there? 32. How many are green? How many are green? 4. I happen to have grabbed a green one. Well done. I had a 4 out of 32 chance. Not good. But I put that crayon down on the ground. I reached back into my bag. How many crayons are in there? 31. How many green ones are still in there? Just 3. See? Dependent events. So what's the key word we're looking for? Replaced versus not replaced. Or there's a strange situation in a case like number 22. They don't say the word replaced or not replaced. Jack had 4 Snicker bars and 8 Mars bars. How many total did he have? 12. He randomly chooses a piece of candy, ate it, then he chose another. So how many events? Last time. Multiple events, Okay, so 2 candy bars. First one, what was the chance that the first one was a Snickers? 4 out of 12, right? What about the second one? 4 out of 12? It doesn't say replaced or not replaced. He ate it. Guys, if you ate it, can you give it back? So this is a not replaced. What you did the first time, absolutely, unless you're disgusting, it absolutely affected the second time. You ate it. It's gone. So how many Snicker bars are left?
3.
And how many bars are left? 11. So that's another way you can tell dependent. Okay? It might not have said replaced or not replaced, but you knew because if it's eaten, it's gone. Yes, but just want to make sure. All right, so that was pretty fast, really, to get through all of that. That's a lot of stuff. Your homework is the even problems on this worksheet. It's 13 problems. 13 problems. Not that bad. 2 through 26 even. I think that's 13. It might be 14. I can't remember how it works. 2 through 26 even. Which one's Tony? Boom. What a stud listener. 2 through 26 even. Xander. Got it? All right. Y'all still got. You got 14 minutes. Is that right? Y'all did better than the last class. Y'all got 14 minutes. Good job, you guys.